All right. Looks like the influx of people has mostly subsided, so I guess we can get started. Um, I figured we could start by talking about a couple of uh, course logistics things. First of all, you might notice that office hours have started being posted on Piazza. So um, there's some UTA office hours, GTA office hours, uh, probably starting this weekend. Um, which is just in time because the second thing that I wanted to bring up is the fact that you are in fact getting your first problem set released today. In fact, I think it should already be up on Brightspace. Um, or maybe I set it to like go live at 9 a.m. or something like that. But either way, it should be live. It's 4 problems long. Um, it is due 1 week from today, so that is June 21st at 11:59 p.m. And remember that you have like five late days if you want to use them. So right now, no one's used any of their late days, so you could turn it in up to the 26th for no penalty, um, at the cost of using all of your late days for the semester. Um, the problem set asks you to write pseudocode in a few different places. I don't really care what the pseudocode looks like. You can just write like Python or C if you want. Um, we're also not going to be very picky about uh, like syntax and stuff for that. So it's really just about like showing that you have the right idea, like the right algorithm. Um, should the pseudocode do error handling? Yeah, so it doesn't really have to worry about error handling and stuff like that. So the intent behind writing the pseudocode is just to like describe an algorithm that you might write. It's not necessarily to like have something that could be transliterated into like runnable C code or whatever. If you have uh, confusion about whether a particular thing is necessary to include or not, you can ask about it on Piazza or in office hours, and TAs will be more than happy to help you, or I'll be happy to help you as well. Um, but yeah, so just don't like worry about the finer details of that too much. So that's the problem set due 1 week from today. Um, the first programming assignment I said would be released on this coming Monday, so the 17th. Um, but since we are a little bit ahead in terms of material, I figured I would release it early. It's still going to be due at the same time, so it's still going to be due 2 weeks from Monday, which is I think July 1st at 11:59 p.m. But this way you'll just have an extra few days to do it. And that one also I think should be live. If you go into Brightspace under programming assignments, you'll see programming assignment one, and then there's also like an assignment submission open for the write-up. So just as a quick reminder, there's going to be 3 programming assignments. For each of them, you will have the opportunity to get up to 10% extra credit on that assignment by submitting a write-up. There's not like a particular format or style that you need to follow in your write-up, but it's really just like if you do like a reflection on what you found interesting, what you found easy or hard, if you did anything like above and beyond that we didn't ask you to do, if you like document your design decisions or whatever, uh, you can feel free to put those into a write-up and submit it for some extra credit. Like I said, up to 10%. And that'll be due at the same time as the programming assignment. We are currently trying to fix up the autograder. So there is an autograder for it on Gradescope. It's not live yet. You probably shouldn't be able to see it. Um, but we are essentially like testing it and stuff like that because all of these PAs are new. So we're testing it, making sure it looks good, and then hopefully sometime this weekend or like by Monday at the latest, that'll be released as well. So you can get a head start on implementing your stuff now, and then you can upload it to Gradescope and see what kind of score you would get. We'll be releasing some test cases as well, so you can like test things locally. But yeah, any questions about the programming assignment or the problem set before we move on to content? Will the input file for the PA be a text file? Okay, so for this one, no, you'll be reading from standard input. Um, the PDF explaining the programming assignment kind of gives like specific details on what the input format and the output format should look like. Um, but yeah, it's gonna read from standard in. You're gonna print a standard out. Future programming assignments will likely have you reading from files as well. Um, but for now, yeah, you can just use scanf and printf. Um, yeah. Also, if there's any like questions once you read the uh the document for the PA, if there's any like clarifications or whatever, feel free to post them on Piazza. If you have a confusion, it's very likely that other people do as well, and so we can like clarify that for everyone. Um, but yeah. All right. If there's no other questions, oh yes, I've had a number of people reach out to me about rescheduling the exam. If you need to reschedule the exam, like if you're not going to be able to make it at the regularly scheduled class time, July 10th, which is a Wednesday, please email me sooner rather than later so that we can figure out a makeup time for you to take it. That's my pitch for that. And I guess we can get started with content. So let me share my screen. There we go. Can people see the Keynote window? Keep the chat open. All right. So we are going to be starting a new topic today. So for the past few days, we've talked about linked lists, stacks, queues, data structures, and stuff. I figured we could sort of veer into the algorithm side of things for a little bit. So yeah, we're going to talk about asymptotic complexity. This is going to cover things like big O notation and all of that. So if you've been looking forward to that, today's your day. If you've not been looking forward to it, I'm sorry, today's not your day. These are, I say, heavily inspired by slides from Professor Coe and Professor Jones. What I really mean is I went through their slides and I like touched them up and reformatted them and made them colorful. But the content is incredibly similar. Essentially the same. The content is essentially the same. Yeah, okay. Let's get started. There we go. Okay, yes, let's get started. Let's start by revisiting our linked lists. Oh, right. And as always, I know we haven't had like a proper lecture for the past couple of days, but feel free to like unmute yourself and shout out or post in the chat or anything if you have a question at any point. Do please interrupt me. I will try to stop a couple of times to ask for questions, but uh, it is better to force me to stop and get things clarified so that everyone understands things as we move forward. Great. Okay. So let's start by revisiting our linked list stuff. Right. So here's the pseudocode for delete head. And I have a couple questions for all of you. How many steps does delete head take? Like, how many steps does delete head take to run? Like, how many lines of code execute or whatever, right? However you want to count steps. For linked list with just one element. 3. I hear a 3. Does everyone agree that it's 3? All right, I'm going to take the lack of dissent as an agreement. Yeah, 3 steps, right? We load the head, we increment the head, and then we free the node that we wanted to delete. What about if our linked list has 10 elements? How many steps does this take? It's still 3. Perfect. Yeah. We load the head, we increment the head, and then we free the node that we wanted to delete. We don't care about all the other stuff that's living in the linked list. So in particular, if my linked list has like some generic n elements, right? How many steps is this procedure going to take? It's always going to take 3 steps, right? On the contrast, let's look at deleting tail. How many steps does delete tail take for a linked list with 1 element? Five. Okay. 1, 2, 3, 4. Yeah, effectively. I mean, I guess strictly speaking, this would get stuck in an infinite loop because head.next is never going to be the thing that we care about. But morally, yes, it should take five steps, right? What about for 10 elements? All right, I hear is still the same. I hear 15. Two different answers. Who's falling in which camp? Or is there a third? Or 14? Oh, I see another 15. 15-ish. Okay, I like 15-ish, right? Because if there's 10 elements, then we've got two steps. We've got the load, the tail, load the head, and then our while loop is going to iterate a bunch of times. Um, I guess it should be uh I don't know. I don't want to count. I can't really count, but it's going to loop a bunch of times. It's going to loop like on the order of 10 times to get to the tail element and then move on, right? Um, yeah. Uh, do you understand why, Heejun? Does checking a condition count as a step? Yeah, so we're gonna assume that like executing the while previous dot next does not equal node to delete line is 1 step. And so every time that condition gets checked, that's 1 step. And then every time the body of the loop runs, that's however many steps the body of the loop is. Um, so it would be like, I don't know, maybe it would be like 25 or something, 23. I don't know, something like that. Yeah. Yep. Yeah. So in particular, the thing we care about is like the thing that's going to change between different calls of this procedure is the number of times that this loop runs for. Because the number of times the loop runs for is somehow dependent on the size of a linked list. And so in general, if I have a linked list with n elements, this is going to run for, let's see, we've got 1, 2, 3, 4, 5 outside of the loop, plus the loop is going to run n minus 1 times, and the loop is 2 steps, so it's 2 times n minus 1 plus 5, so that's 2n plus 3 or something like that, right? So if I have a linked list with n elements, delete tail is going to take 2n plus 3 steps, whereas delete head is always going to take 3 steps, right? So this is like hopefully not a surprise. This is not new information. We talked about this when we were writing our linked lists, or when we were implementing our linked lists, when we were implementing queues. We talked about why we want to insert at the tail and delete at the head. And then I sort of promised that eventually we would get some more precise language to describe this. Today is the day that we get that more precise language. -1 is from the fall condition. -1 is from the fail condition. Oh, and -1, yeah, because we loop until we get to just before the tail, right? It's 2 times the quantity n-1 because the loop runs for n-1 iterations. If there's 3 elements, then we have to step through 2 things to get to the element just before the tail, right? So it's 2 parentheses n-1 plus 5. I guess the people on the recording can't see that. Ooh, you know what? I have just the tool for this. Or memento. Oh, yeah, buddy. Here we go. It is. So this is 1, 2, 3, 4. That's right. Pen is coming out. And then this is 2 steps, right? And then this loop is going to run n-1 times, right? So it's going to be 2 times n-1. two elements in the loop, or like two lines in the loop, n minus one iterations, plus the extra five is 2n plus three. Yeah, there we go. All right, cool. Okay, let's do this a little bit more carefully with maybe a simpler loop, right? So I have some C code here that adds up the numbers from 1 to n. Oh, from 0 to it adds up the numbers from 1 to n. Okay, don't come at me about my like bounds checkings or off by one errors or whatever. Um, so the question I want to pose here is, oh, n is just n. It's just a number. It's just how long this loop is going to run for, right? It's an input, right? Everything we're going to do is going to be parameterized on some kind of like problem size. So n in this case is the problem size, right? Um, so I guess what I really want to say is how long is this going to run for in terms of n? Um, so we can do this by sort of like there's four lines. We can assign each line some kind of like cost, right? This could be like a latency. This could be like the total number of instructions. This could be whatever we care about. This could be like milliseconds. I don't know. So we have C1, C2, C3, and C4, right? And then we can just look at how many times each line executes, right? So line one, int total equals 0, initializing this variable. How many times does that execute? If I run this snippet of code, one. Thank you. Great. All right, line two is the header of this for loop. So for int I equals 0, I is less than n, I plus plus. How many times does that run? N plus one. Excellent. Thank you. All right. Now line three, total plus equals I. How many times do we expect that to run for? N. Perfect. And then return total at the end. One. Excellent. All right. So we filled out this table, right? Lines one and four run once. Line two runs n plus one times. Line three runs n times. Note, line two runs n plus one times because we have n iterations inside the loop, and then we have the extra time that we check. We notice that I equals n, and then we skip past it, right? So if you're like stepping through this in GDB or something like that, that's the number of times it would trigger. The plus one's going to turn out not to matter, but it's important to keep it there. So we add all of this up. We get C1, like the total amount of time that this takes is C1 plus n plus 1 times C2 plus n times C3 plus 1 times C4. If I rearrange my terms, I get something times n plus something else, right? So morally speaking, this is basically linear, right? I mean, I don't know, it's affine or whatever. It's more complicated than just it takes n steps, but it's effectively it's like some linear function of n, right? That one was pretty easy. Let's maybe look at a more complicated one. So here I want to go from 1 to n. I want to add up all the squares that are divisible by either 3 or 7. Okay. Um, you might say this is contrived. I would say yes, it is contrived. Um, but I don't know, deal with it. Okay. So how many times does the first line run for? Yep, just the once. What about line two, the header of the for loop? N plus one. Thank you. What about the first branch of that if statement, the I squared mod 3 equals 0? That runs n times. What about the second part, I squared mod 7 equals 0? About two-thirds of n. Yeah. Um, correct. And then what about line 7, total plus equals I squared? Excellent. Thank you. Perfect. Yes. It's about one third plus one seventh minus 1/21st of n. It's that, right? Um, Also, I realized that this has a typo. The return should be outside of the for loop. Pretend it is. I wrote these at like midnight last night, so give me a break. But yeah, um, we no longer have like nice expressions like, oh, it's just n or n plus one or whatever. But we can still tally up all of the numbers. And we see that the total is C1 plus n plus 1 times C2 plus n times C3 plus the ceiling of 2n over 3 times C4 plus that whole expression times C5 plus C6. And if you rearrange everything, you put all the n's together, you sort of like put them over a common denominator, you end up getting something that's still basically linear in n. Again, I don't want to like do the arithmetic involved for this, but it's hopefully you believe me, right? There's a bunch of terms with a factor of n. There's nothing with like n squared or anything like that, and then there's some like constant terms at the end. So we have something else that's basically linear in n, right? But it is a different formula. Like this will take a different amount of time to run. Um, so we've got sort of like two ways of thinking about uh, the runtime of these different programs, right? Like in one sense, they both have a loop. They both go from zero to like both loops go from 0 to n, and they do some work inside the loop or inside the body of the loop. But in another sense, they do like different amounts of work. So it's, I don't know, maybe interesting to think about. Okay, so I want to maybe use this to motivate the idea of asymptotic growth. So first of all, we computed two different formulas, right? On the last slide and the slide before that. One of them was very nice, one of them was very not. Um, how valuable are these formulas really? Like if you write a piece of code and you want to like understand how efficient it is, or like you design some algorithm and you want to know like, is this the best possible algorithm? Can I do better? Is this algorithm better than the other one or whatever? How useful is actually computing this formula going to be in terms of telling you what you need to know? Um, One negative I'll point out, this was kind of annoying to compute, right? The first one was fine, but the second one, if Robert wasn't completely on point with all of these fractions, it would have been awful, right? And then also it is just difficult to parse, right? You've got like ceilings and floors everywhere. You've got like random fractions all over the place. I don't know, like it's very difficult to like Robert goaded. Yes, thank you very much. It's very difficult to like look at this formula and sort of like understand what it tells you or like get any like real insights about the algorithm. Um, the other thing is the actual numbers depend a lot on the concrete values we choose, right? So we did everything in terms of like the cost of running line one, the cost of running line two. But on different, I don't know, like different hardware platforms, different compilers, different languages, whatever, these numbers might change a lot, right? And so for some instantiation of C1 and C2, one thing might be really fast. For another instantiation, it might be really slow. Um, so even if we do compute the formulas, even if we do like go through all of the work to like parse them and understand them, they're still parameterized on like so many different things that it's sort of like, okay, we could like model all of this. We could try to plug in actual numbers and we could get some sort of result back, but that seems like a lot of work. That being said, though, they're not useless, right? They provide some good heuristics. So for example, when we did kind of a hand wavy version of this on the first slide with delete head versus delete tail, right? We noticed that delete head is constant, like the number of steps that the procedure takes is constant, no matter what the size of the list is, compared to delete tail, which is roughly linear in the size of the list, right? It ended up being like 2n plus 3 or something like that. And so even if we don't look at the exact formulas or if we don't plug in like actual concrete numbers or whatever, we can kind of get the right vibes, right? Like something that takes a constant number of steps no matter what is generally going to be better than something that takes a linear number of steps. Something that takes a quadratic number of steps is probably going to be worse than something that takes a linear number of steps, right? Like if I had two nested loops or something like that. Um, so we care about the formulas, we just don't care about the exact formulas, right? And so the conclusion that I'm hoping to lead you towards here is that we don't care about the actual function. The only thing we care about is how fast it grows, right? So 2n plus 3 and C1 plus C2n plus C3 plus C4, like whatever, like all of those things, they all grow roughly at the same speed because they all grow like with n. Um, the constant function 3 doesn't grow at all, right? So the thing we care about is like the rate of growth, not the actual formula. Um, and the rate of growth, I'm going to call this the asymptotic behavior, right? So if you took like a calculus class or something, you might think of asymptotes as like a line that a function approaches as it goes out to infinity. That's essentially what we're talking about here, except for instead of like a line or a particular value, it's going to like we're going to talk about how as n goes to infinity, the behavior of our function looks a lot like some other function or is like bounded by some other function or something like that. Um, so maybe if you want to like tie this back to a math class you've taken or something like that. And in particular, the thing that the asymptotic behavior is going to tell us about is how does our algorithm respond to a growing input size, right? So it's important to know that we are in fact throwing away a lot of information by looking at this, right? We're throwing away all of those constants. We're throwing away like the coefficients in front of n. We're throwing away, as you'll see later, we're throwing away a ton of information. So this isn't actually going to tell us how fast this particular program is going to take to run on a particular input. It's going to tell us how well does our algorithm scale, right? Something to keep in mind. Finally, we can get into big O notation. So this is going to be kind of a, I don't know, like a technical slide. I'm going to try to break it down and like give some intuition because I think formulas, just like a first order logic sentence is maybe not the most clear thing. So for definition, given two functions, f of n and g of n, we say f of n equals big O of g of n, is pronounced f is of order g, if we can find some constants c and n naught, such that for all n greater than or equal to n naught, f of n is less than or equal to c times g of n. All right. That's a formula, right? If you can find constants and you can prove that that inequality holds for all n greater than or equal to n of 0 or n sub 0, you can claim that f is of order g. Intuitively, as I promised. You can think of this as like c times g of n is an upper bound for f of n, right? It's like f of n is bounded from above by this scaled version of g of n. But in particular, it's an upper bound after a certain point, right? We also maybe want to say something like f grows no faster than g, up to a constant factor, right? So it might be like, it might grow no faster than 2 times g or something, but that's still fine, right? It's just a constant factor. The important thing to note is that we don't care what happens for very small n, right? So f might be some like very crazy function that starts off doing some like really weird stuff. And like later on, it kind of like figures its stuff out and like does something more normal. Usually when we do this, we're going to want g to be like some easier function, something that's a lot easier to understand, and we can use g to try to understand f. But like the definition works for just about anything, right? That's a lot of words. You can look at a picture. This is a figure that I have graciously liberated from the aforementioned slides, by which you should understand that I took a screenshot and pasted it in here and then annotated it a little bit. So, right, the red line is f of n, the green line is g of n, the blue line is g of n scaled up by some constant c. A couple things I want to draw your attention to here. First of all, you'll notice that for like small values of n, f kind of like I said, it can't figure itself out. It goes up, it goes down. It crosses both thresholds all the time. And we don't really care, right? We don't care what happens for small values of n. It's just after n naught that it kind of settles into this nicer pattern. The other thing is we don't really care about scaling g up by a constant, right? So yeah, we could make this constant bigger if we wanted. Up to a constant factor is fine. And so finally, the thing that you should maybe take away from knowing that f is of order g is that f and g eventually have the same shape, or rather like the shape of f is eventually bounded from above by the shape of g, right? So Again, this isn't really telling you anything about the actual values of the functions, right? Because our constant could be something huge. And so if we're saying that it's bounded from above, it could be bounded from above by like 10 million times g, right? So f might still have really, really big numbers involved. It's just the rate at which it grows is not going to be faster than the rate at which g grows. All right, attendance poll. What are some limitations of big O? So we kind of talked about big O. I kind of alluded to some of these limitations before, but why might we want to consider other factors when we're reasoning about our algorithms? Um, I guess since we're doing this synchronously in class, I might wait a minute or two for people to drop their answers in the chat. The poll should already be up on Brightspace, so if you want, you can go submit it now, or you can wait till after class. I don't really care. Any thoughts? On a sorting algorithm, the runtime is not always the same for the same n. Yes, yeah, exactly, right? So um, our complexity might tell us something like it might tell us some vibes of what it's going to look like for a particular n, but the actual runtime is going to vary a lot. And yes, exactly, it ignores constants in lower order terms, right? Something that looks like 2n and something like 100n is going to be the same. They're both going to be linear. It's a general solution. Yeah, it's very generic, right? So um, these are all very good points. I think the moral of the story that I want to kind of impart on you here is, and we'll talk more about this, right? So if you don't yet have the intuition for it, that's fine. There are plenty of slides that will hopefully help you develop that. Um, an algorithm that has a better like big O complexity is not always necessarily going to be faster than an algorithm with a worse complexity. It's just necessarily going to scale slightly better, right? But the input size on which it does better might be something ridiculous. So I encourage you to look up this thing called galactic algorithms. There's like a Wikipedia page for it. I think my favorite one is like if you're multiplying two like n-digit numbers, the usual algorithm we have for multiplying things that you like, I don't know, like learn in grade school or whatever, right? Like you do the ones and the tens and all that. That's like O of n squared roughly. Um, there is a way to do it in O of n log n. If you take a 1,729 dimensional fast Fourier transform of the problem and it's really only faster for numbers that like can't be expressed even if we wrote one digit on every proton of the universe or something ridiculous like that. So I'm gonna write this down, but I I encourage you to look at galactic algorithms. Yeah, all right. That's for the people watching the recording. Okay. All right, let's move on. Let's talk about big O in practice. So, like I said, usually f of n is some very complicated formula, right? We've like analyzed our for loop. We've looked at like what these branching conditions mean, how often each line is going to run, and stuff like that. It's very like it's ridiculous. G of n is a function that's a lot easier to understand. How do we show that f of n equals big O of g of n? Like, how do we show that f is of order g? Well, there's usually two ways. One is we can explicitly compute the values of these constants and show that this inequality holds. This is in general kind of annoying, and in particular also requires like we're like working with concrete things here, so it requires like an explicit formula for f of n, which means that we have to like go through all of the work of computing the for loop, like doing all of that, which is even worse. I mean, maybe you enjoy doing it. I certainly don't. But it's something that you can do, right? If you want to like do a proof on some new algorithm or something like that. The other thing is we can use some known properties of big O to try to simplify the calculation. And so for most of the rest of the lecture, I'm hopefully going to like give you some intuition for like what these properties look like and how you might kind of um, analyze things using these properties. So what have we got? First of all, it's reflexive, right? F is always of order F. And to see this, you can just let C equal 1 and not equal 0. Um, yeah, F grows exactly as fast as F grows. That's maybe not particularly useful, but it's true. Transitive. If F is bounded by above, if F is bounded from above by G and G is bounded above by H, then F is bounded above by H, right? So if we can like break our problem into multiple smaller pieces, then we can show like each piece and we can kind of compose them together like this. Multiplicative. This one's very useful. If I have two functions, f1 and f2, and I know f1 is of order g1 and f2 is of order g2, you can show that f1 times f2 is of order g1 times g2. In other words, like the order of the product is the product of the orders, right? And the way to see this is I think you let n naught be the max of the two n naughts and you let c be the product of the constants. Um, but yeah, so this is very nice, right? If I have some like weird complicated function, I can like factor it into smaller pieces, try to understand each piece, and then just compose them back together. And then also, as was sort of alluded to earlier, lower order terms don't matter, right? So if f is of order g and g is of order h, then f plus g is still of order h. So for example, something like 5n plus 100, 5n you can see is like order n. 100 is O of 1 because it's just a constant. But since I'm adding those together, I take the highest order term there, which is O of n. So 5n plus 100 is O of n. Let's step through like a petting zoo of functions, I guess. We've got constants, O of 1. These are great. If you've got something that runs in constant time, you can throw whatever you want at it. It's never gonna like, it's always gonna be great. Logarithmic, which is like O of log n. Important to note that the base of the logarithm doesn't matter. So like log base b is O of log base c of n for all values b and c. This is because you can do like the base change thing, and the base change turns into a constant. You factor that out, and it all works. A lot of times you'll see logarithmic stuff with like algorithms that like recursively decompose your problem. And we'll talk about that next week. Linear is like O of n. So you have to scan through an entire array. That's almost always going to be linear. If you've got a for loop, that's probably going to look something linear. Worth noting that if you have something that's like a polynomial in a logarithm, that also ends up being linear. N log n, a lot of sorting algorithms are n log n. I don't have a fancy name for this. It's just n log n. Right, then we've got polynomial. So n to the k. Important to note that the exponent matters. So if k1 is bigger than k2, then n to the k1 is not of order n to the k2. So in general, like n squared or n cubed is going to grow faster than n squared, and n to the fourth is going to grow faster than n cubed, and so on. Right. So the exponent here matters, unlike log where the base doesn't matter. Then we've got exponentials. So this is k to the n, right? So n to the k, n was our input size, k is a constant. Exponential, k is a constant, n is the input size, but now it's in the exponent. Here, the base matters, right? So 2 to the n grows slower than 3 to the n, which grows slower than 4 to the n, and so on. Crucially, this also means that like sticking a constant in front of the n does in fact change the complexity here, whereas it doesn't for linear, right? So like big O complexity doesn't distribute across exponents. And there's combinatorial and factorial. This is usually really bad. If you're looking at like all possible permutations of something, you'll get something combinatorial. A lot of times you'll have like you'll be given a problem and you'll think of like what's the most like naive possible algorithm you could throw at it. And that'll be something like O of n factorial. And then you'll try to like work your way better, like work your way down from there and try to get something better. And then I like to call this one confused screaming because it's O of n to the n. Like it's worse than factorial. I can't think of a reason you would come across this unless you were purposely trying to get something really, really bad. If you do find an instance of this in the real world, please let me know. I think it would be cool to know about. Anyway, good to know. if you're analyzing an algorithm, a lot of times it's going to fall into one of these buckets. And then of course, each thing is big O of the next thing, right? So anything that's constant is also big O of log n, is also big O of n. Like it goes up, but it doesn't go down. Okay, on that note, some more classifications. Um, we have big O. This is big omega. Yep, big omega. F of n is big omega of g of n. If there's some c and n naught such that it's bounded from below, that's kind of the converse of big O. In particular, if Fn is big O of Gn, then Gn is big omega of Fn. Pretend that's an n. That's not a g. Uh, yeah. So you can kind of reason about it in both ways. Um, Normally, right, if you have an algorithm, you care about like how bad could it be, like how long could it take to run, not how good it could be, but it's nice to have the language to talk about both. So intuitively, this is like F grows at least as fast as G, right? Up to a constant factor as always. The other one that we are going to care a lot more about is big theta. So F of n is big theta of G of n if it's both big O and big omega, right? So this is like F is bounded from above by G and from below by G. Importantly, the constants don't have to be the same, right? So it can be bounded from above by like 3 times G and bounded from below by like 2 times G, and that's fine. It doesn't have to be the same constant, right? So F doesn't have to be exactly equal to G. It just has to like somehow be like sandwiched between these. Um, and so the intuition for this is that F and G exhibit the same asymptotic behavior. Usually this is what we care about, right? Because if you have something like n plus 3, that is in fact big O of 2 to the n, right? It's totally bounded above by an exponential function. But that's not helpful, right? Like you that doesn't tell you anything useful about the algorithm. But it's only big theta of n, right? And so that's sort of what you care about, like the fact that it's morally speaking linear. Okay. Any questions on the stuff that I've gone through so far? And it was kind of a whirlwind of like definitions and examples. Before I bombard you with any more stuff, can there be more than one relevant size variable? I love this question because that's exactly what I'm going to talk about on the next on the next slide. Um, yes, there can. I guess we'll do that. Great, awesome. Did you read my slides ahead of time? I posted them last night. Uh, no, you didn't. Okay, that's fine. Just have ESP. That's okay. Okay, let's talk about multiplying two matrices, right? Here's another example. I'm not going to go through the whole like the table with all of the things here. I'm just going to kind of go based off of vibes, right? So first of all, you'll notice here that the number of steps depends on n, m, and p, right? So I've got an n by P matrix called A. I've got a P by M matrix called B. I'm going to multiply these together into an N by M matrix called C. This is a triply nested for loop, right? So F now depends on 3 different variables. If I look at how often each for loop runs, the I for loop is going to run N plus 1 times. The J for loop is going to run M plus 1 times each time it runs. But because it's going to like, because we're going to enter that for loop N plus 1 times, the total number of times that line is going to run is N plus 1 times M plus 1. In the same way, line 3 is going to be N plus 1 times M plus 1. Oh, there's extra plus ones there. Forgive me. Line 4 is going to be like, it's going to be P plus 1 executions of that loop header each time we get to that, but we're getting to that like roughly N times M times. And so it's going to be that. And then the thing on the inside is going to be N times N plus times P, right? And so the total is this whole thing. I realized that I said K in the total formula. That should be a P. K is the like induction variable. But hopefully the point here is clear, right? So I can drop everything but the highest order terms. I can factor everything out, throw away the constants, and I end up with big O of NMP. Uh, Let me correct this. Right? There we go. Oh, this is not helpful. There we go. All right. So it's linear in n, it's linear in m, it's linear in k, but overall it's polynomial, right? If I were to think of m and k being fixed as constants, I could say this is linear, it's O of n, but it's, somehow it's polynomial. It's like a cubic, right? Um, so yeah, hopefully that answers your question about more than one relevant size variable. Um, hopefully it doesn't raise too many other questions. Does it make sense? Okay. Yes. Should we try to avoid nesting loops then? Yeah. Absolutely. Right. So as a heuristic, for every nested loop that runs n times, the overall complexity is going to pick up a factor of n. So we've got like a triply nested loop where each loop runs for n iterations. That's going to be a complexity of like O of n cubed, right? So in general, if you've got something polynomial, like usually you'll see polynomial time algorithms, or like you'll see something like O of n to the k if you've got like k nested for loops, or it's going to like somehow be convertible into like k nested for loops. Um, so yeah, that's a good heuristic for analyzing this stuff. Because I know how much everyone loves examples, I'm going to immediately make this more complicated. So here's a snippet of code that tests to see if an array contains an element. Uh, okay. So first question I want to pose for you is how many times does this loop run, right? So I've got a for loop from lines 1 to 5. How many times is that loop going to run? Anyone have any thoughts? N plus 1 times if it's excluded or at the end, otherwise less than n. Min index of item n plus 1. Both of those are absolutely correct, right? So the answer is somehow it depends, right? If array of 0, if the value is an array of 0, then it's just going to run once, right? It's going to enter the loop. It's going to say yes, array of 0 equals value. It's going to return true, and it's going to break out of the loop. If value is not in the array, it's going to run n plus 1 times because it has to go through the entire array, and then it's going to like go to the end, and then it's going to hit return false, right? Um, and so it's sort of like if the value is at the beginning, it's constant time. If the value is at the end or like not in the array, it's going to be linear time. But if you give me this algorithm, right, what do I call it? Do I call it constant or do I call it linear? Um, so in particular, if we think of like the best case scenario here, which is the values at the very beginning of the array, this is sort of constant time. So it's like best case constant, right? Um, the worst case scenario is it's not in the array at all, which means it runs n plus 1 times. So it's like worst case linear, right? So if you've heard these terms, like this is like best case logarithmic or something like that, that's sort of what it's talking about, right? Like if the runtime of the algorithm depends on the input, what's the best possible input and what's the complexity on that particular input or on that like class of inputs or whatever. So you've got a best case and a worst case, but it would be nice to have some kind of like average case, right? So like if I want to sort of like summarize this algorithm, if I want to say like if I don't know anything about my array, if I don't know anything about my value, what can I expect the complexity of this algorithm to be, right? So this is sort of what I care about for the average case. It turns out this can be a very hard question unless we analyze it probabilistically, right? Because we don't know what the input's going to be. So we sort of have to like guess, I guess, sort of, right? Um, and so we can consider running the algorithm on a uniformly random list, right? We have to say uniformly random because we don't have any like prior distribution over what our lists might look like. If we do, then we use that distribution and then all of this math changes. Um, what's the probability in a like uniformly random list? What's the probability that the value is at the first element of the array at index 0? 1 over n, kind of, not quite. Assuming it's somewhere in the list. It might not be in the list though, right? I'm going to call this 1 over n plus 1 because there's n different places it could be in the list or it could not be in the list at all. So I'm going to call it 1 over n plus 1. Similarly, the probability that it's at index 1, it's going to be 1 over n plus 1. The probability that it's not in the array at all is going to be 1 over n plus 1, right? Now, for each of these cases, let's analyze the total number of steps it's going to take, right? So if it's at the beginning of the list, if it's at index 0, our algorithm is going to take 1 step plus some constant number of steps for like initializing and returning and whatever, which I don't really care about. If it's at position 2 in the array, it's going to take 2 steps. If it's not in the array at all, it's going to take n plus 1 steps, right? In general, if it's at position I in the array, it's going to take I plus 1 steps, right? And so we can look at like the expected value. If you've taken 302 or some equivalent like probability class or like random variables class or something, this formula will look familiar. But the idea is we look at all possibilities. We look at how many steps it's going to take in that particular possibility and multiply it by the probability of that happening. Why is the chance it isn't in the array the same as it being in some index? To sort of simplify this, right? Um, if we so really this is like I'm uh randomly sampling from my space of lists in a particular way, right? Because there's I guess what I want to say is I'm not randomly sampling the lists, I'm randomly sampling all the possible execution traces, right? So and I'm like assuming that every trace is uniformly distributed because I don't have any prior distribution over the traces, right? So there's n plus 1 possible um program traces, right? It could enter the for loop and immediately exit. It could enter the for loop once and then exit. It could enter the for loop n times and then exit, or it could enter the for like there's n plus 1 possibilities for the number of steps that the program could run for. Cool. It's a little bit hand wavy, but to make it precise is a bit more complicated. Um, so yeah, so this is our formula for like the expected total number of steps. So the probability that we're in trace I times the cost of trace I. If we expand this out, we get all the probabilities are 1 over n plus 1. The cost of I is I plus 1. So we sum up for I equals 0 to n of I plus 1 over n plus 1. You work that out, you get this thing. You cancel out the n plus 1, you get n plus 2 over 2. And you can see n plus 2 over 2 is big O of n, right? So in particular, best case scenario, it's constant time. Worst case scenario, it's linear time. Average case scenario, it's still linear time, but slightly faster, right? It's like roughly twice as fast in the average case. Um, so that's all I have. Are there any questions? I know we went through a lot of material. We're going to keep talking about complexity analysis. We're going to talk about like space complexity. We're going to look at more precise ways to analyze like iterative and recursive algorithms um, in the next week. But this was sort of maybe an introductory lecture. Uh, any questions? Any clarifications? Did I post the last modified linked list.c to Brightspace? Oh, yes, I will do that. Well, if there's nothing else, happy Friday, everyone. I figure I'll like give you, I went over time the past few days, so I'll like give you these minutes back, maybe let you out of here early. Feel free to stick around if you do have more questions. Don't forget, um, assignment, right? Problem set released today is due 1 week from today. Um, Programming assignment probably released today. The poll question is like the limitations of big O complexity. Um, so uh, what does big O not tell you about, right? Um, yeah, and the poll should already be active on Brightspace, so you should be able to submit it there. Um, all right, cool. Have a good weekend.